see this intense bright region if a big flare was going off. And I don't know exactly what that would do to the black dot of Venus. It might cause us to not be able to see it anymore if it was transiting right over that flare. But we, since we haven't seen it, we don't know.
A flare of that magnitude would cause magnetosference, would it not?
It sure would. It sure would. Magnetosference. If a flare is on the right spot of the sun, directed towards the Earth, then yes.
Hey, Blair, why did everybody laugh at magnetosference?
It's a laugh of jealousy because the scientific community did not discover this great word, magnetosference, that I've coined, but hopefully they'll adopt it. But magnetosference is my favorite word to describe what happens when solar radiation impacts or affects the Earth's atmosphere, or in this case, Venusian magnetosference, when it impacts Venus's atmosphere.
Well, I was going to say, and this is a bit of speculation on my part because I'm not a planetary atmospheric scientist, but one of the things that's very important is flares have a direct impact on the Earth's atmosphere. They change the ionization of the outer atmosphere. Venus has a very thick, very exciting, and interesting atmosphere. So you can imagine that if a really strong flare lights up the back or around Venus's atmosphere, we may be able to measure some of the effects. And I'll let some of the planetary scientists speak on this.
Yeah, Alex. It's interesting that Earth has a global magnetic field, right? Which is what we mean by magnetosphere, right? It's basically the Earth is a magnet, and so it deflects those charged particles that come from the sun. Venus does not have a global magnetic field, right? And so that charged particle radiation from the sun, the solar wind, which goes 24/7, but gets excited by solar activity like flares and gets faster and more energetic, that goes directly onto that thick, dense atmosphere of Venus without the shielding provided by a global magnetic field.
Actually, I was hoping you wouldn't bring this up because that actually came up years ago when I said I was challenged embarrassingly on the NASA Edge set when I was asked whether it would happen on certain planets that apparently don't have our magnetosphere, and I thought they all did. So I got to cry foul on that one. But nonetheless, what bounces around Venus probably comes and hits us, and that's definitely technically textbook magnetosference.
Well, I was going to add that one of the things that I would think would be of use is, not only does the energy, the light from the flare, not just the particles, but the light from the flare affect our atmosphere. This is an important study for climate science. It's very important for us to understand the impact and the amount of energy that goes into our atmosphere and how that relates to the energy budget and climate, including how that's affected by solar activity, which is much higher energy. So I'm guessing Venus is a very important place to study that kind of phenomenon.
I tell you what, just real quick, if you could see us huddling around talking about solar flares and planets and the transit, it's like being in a freshman astronomy class.
Yeah, and I felt uncomfortable then.
Speaking of astronomy class, Lou, what did you go over with your students this past semester in advance of the Venus transit?
Oh, well, this was Astronomy 100 at Marymount University for non-majors. So people took the class for all kinds of reasons, and it makes it both exciting and a challenge to teach. We talked about the transit. We talked about parallax. We talked about how to view the transit. Go to venustransit.nasa.gov. Even one of my students, hopefully they're watching today, is holding a transit party. And we talked about why this is all important.
Even more important, back in February when we were out here testing for this Venus transit, you were actually Skyping with your class about the transit.
That's right. We couldn't do this in 1882, but we could. But we did that in 2004. We can do it now. We're a connected planet now, so information gets around real fast.
One assignment we had, wasn't it part of extra credit if all your students would go to the website and our website, NASA Edge, www.nasa.gov/NASA Edge, and download all 90-plus episode of NASA Edge as part of their grade?
Perhaps I did allude to that. I'll get back to you on that.
Hey, we have another question from our viewers. This one's from Anna. Can you explain why the transit appears at the top or the bottom of the screen?
Well, it really just depends on how the telescope that the camera is attached to is oriented. And for a while there, I guess we had some different telescopes with different cameras and filters. They were oriented different ways. And I think that was cleared up now. Is that correct, guys?
That is correct.
Okay, so that's really why it was changing, because it kind of depends on how you're facing when you look at it, how these telescopes were turned when they were looking up at the sun. So that was really the reason.
You know, this is very historic, an event here at Mauna Kea, because we're actually able to see the transit from this location. But Lou, tell us, in 2004, that wasn't possible.
That's right. It turns out that it's not an integer number of days between transits. So the Earth has turned a fraction more or less between these transit pairs. And in 2004, where, for example, on the East Coast, where I live, in 2004 we saw the transit in progress as the sun was rising. But in 2012, on the East Coast of the United States, we're seeing the transit from its beginning as the sun is setting. Some places on Earth won't see the transit at all. So it just depends on which transit you're viewing and where the Earth is oriented at the time of transit.
Well, so there's a question about how often Mercury transits.
Yes. Is there a transit of Mercury, and how often is it?
Yeah, Mercury, orbits inside the orbit of Venus, right? So Earth is third rock from the sun, right?
Good plug. Yeah.
And Venus is second rock from the sun, and Mercury is the first rock from the sun. So Mercury, for reasons involving the laws of physics, goes faster around, right? And so its transit of the sun, and for geometric reasons and its speed of orbit, will actually happen more often, right? It occurs more often than the Venus transit. But it's more challenging to see, I believe, right? Because the little dot is even smaller of Mercury on the disk of the sun.
Well, it does have a really important relationship with the Venus transit, because the initial idea of determining distance to the sun with parallax was actually originally suggested with Mercury. But what Halley said was, well, the planet is much closer, and when you're using parallax, things that are closer have a much larger apparent spread, and it makes it easier to actually make an accurate calculation.
That's right. Mercury transits occur roughly 10 times per century. So that's a lot more frequently than Venus transits. And the next Mercury transit is not that far away. It's in 2016. So we can all start preparing right now.
Okay, I got a question, okay? I don't know if you can answer it. When do you think, and this is just hypothetical, when do you think someone will actually see an Earth transit from Mars? And is that possible?
I think that we are going to go to Mars. And so I think that's a very interesting possibility. I haven't done the calculation though, Lou. Here we go.
Well, it turns out that in 2084, there will be an Earth transit as seen from Mars. So that's how long we have.
Lou, do you have a computer in your head? You can see the calculations being done right away.
Surface of Mars.
Well, I mean,
make sure people know that we are. Yeah, we be accurate. We are at altitude. Check Lou's numbers.
Well, again, this is really important, because there actually is kind of an interesting relationship between the journeys to see the transit and Mars. Because again, back in the 1800s, the astronauts of the day were the explorers who were traveling to places unknown. They didn't have maps. They didn't have Google. They couldn't find their way around the world, and they were going to unknown, scary places that took the same amount of time that it would take us to get to Mars. And so that's just an example of the early explorers, the early astronauts, and we're the next step to that.
That's right, Alex. And I misspoke a little bit. I said that's how long we have to get to Mars. We've already been to Mars with robots, taking fabulous data, fabulous images. And so we're sitting on the surface of Mars with robotic observers right now.
And I want to say that when you drive up to the summit of Mauna Kea, if you never make it to the moon or Mars, this summit is very much like you see the pictures of those environments. It's a really extraordinary cinder cones, red, lack of vegetation. It's really like being on Mars.
All right, we do have another question from a viewer, from Dempsey. And the question is, this is actually a viewing question. Would you be able to view the transit with a pinhole viewer?
Oh, absolutely. I mean, as long as you use it properly. I mean, don't point it at the sun. You use it to project the sun through that pinhole onto the wall and kind of move it around so you can get the right position so that you can get that image of the sun large enough, and then you should be able to see that spot of Venus on there. And you can just make a pinhole by punching a little hole in a piece of paper, a piece of cardboard, or you can do things like lace your fingers together and use that as your